If you recall yesterday, we started learning about partial fraction decomposition. Partial fraction decomposition. This is what we have to deal with when we have a denominator that is greater than degree 2 or is quadratic with real zeros like we have here. So degree 2, but it's quadratic with real zeros. So the x squared minus 2x minus 3, we know it's quadratic with real zeros because that is factorable to x plus 1, x minus 3. So the first step is deciding that you have to do this process. By looking at the nature of your zeros. Then we set up the decomposition. We set up the form of the decomposition that we want. Each factor of the denominator contributes a term to the decomposition. So x plus 1 is a factor. That's one of our terms with a denominator of x plus 1. X minus 3 is a factor. That's got to be one of the terms in our decomposition. The degree of the numerator is always 1 less than the degree of the denominator in the decomposition. So that means our denominators in the decomposition are linear. So in the numerator, or degree 1, so the numerator will have degree 0. Then all we have to do is figure out what a and b need to be to make this work. We do that just by adding up the fractions and comparing the coefficients. So we generate a linear system by equating the coefficients. So we have, when we add, we get the common denominator a times x minus 3 plus b times x plus 1. When we multiply all that out, so ax minus 3a plus bx plus 1b. And then we just rearrange. We gather the x terms and then we gather the constant terms. Since this fraction must equal our original fraction, that means the coefficient of x, a plus b, must be equal to the other coefficient of x, 7. Since these two fractions are equal, this constant, negative 3a plus b, must equal our original constant, negative 13. This leads to a system of equations. I can't remember if I solved this yesterday. I think I just wrote down what the answer was because we knew that the answer was 2 and 5. That's where this came from. But usually, for this kind of partial fraction decomposition, one of them will have a plus b equals constant. So this addition method, a variation on solving the system with a matrix, is pretty effective. So I'll multiply the second equation by -1 and add it to the first equation. So this tells us that a is equal to 5, b is eventually 2. Now we have 7x minus 13 over x squared minus 2x minus 3 is equal to 5 over x plus 1 plus 2 over x minus 3. And yesterday we talked about why that was useful when we're doing integration. Like, oh, that is awesome for integration because the integral of a over x plus 1 is a times the natural log of x plus 1. So breaking down into these terms is very useful. But if I recall correctly, I promised you a shortcut to avoiding solving the linear system. So the shortcut starts here as soon as we put the two fractions together. The shortcut goes like this. This is what I call this shortcut. I say, just grab the numerators. You're going to see why we don't want the denominators around. We're just going to grab the numerators, pull the numerators aside. So the shortcut is grab the numerators. I don't know what the official name for this shortcut is, but I call it grab the numerators. Specifically because it reminds us that we're avoiding the denominators with what we're about to do. I'm going to grab the numerator 7x plus minus 13. And this has to equal a times x minus 3 plus b times x plus 1. And we're like, oh, don't worry, denominators. Just chill for a minute. We're just going to run out and buy cigarettes. We'll be right back. Here's the reason that we just want to grab the numerators. We want to make this equation, this equation needs to be true for all the x except 3 and -1. Because in our original, we don't get to have x equals -1 and x equals 3 because of those denominators. But we left them at home. And we're just hanging out with our numerator friends, where it's perfectly acceptable for x to be 3. And look how convenient it is if we let x equal 3. It takes out anything to do with a. So whatever will make these factors 0, we're just going to plug in a value because it will get rid of a or b. So we're going to let x equal 3. Then we get 7 times 3 minus 13. Don't forget to put it over here. And then we see the cool thing that happens. 3 minus 3. I forgot to write b. Could have written it at the end. So the reason that this shortcut is super effective is that we don't set up a system of equations, a system of 2 equations with 2 unknowns. We get an equation with just 1 unknown. This shortcut takes out one of our numerators. So we get 21 minus 13, and over here b, and we get 4b. And then 21 minus 13 is 8. So this tells us that b is equal to 2. Then we'll just do this again for another very convenient value like -1. So this conveniently takes b out of the equation. I could have filled in 2 for b, but it would have made more sense to have a 2 in for the b. It's getting multiplied by 0 anyway, so we're not really concerned. And then we'll end up with -4a. And then we'll have equals -20. And so a is still 5. So this is a shortcut in partial fraction decomposition called grab the numerators. The reason that we want to just grab the numerators is that we can't have x equal 3 or x equal -1 in our original. That will make the denominator 0. We'd be all dividing by 0. Math cops come bust down our door. And we spend the night in jail. Math jail. Most of the occupants of math jail are there because they divided by 0. Any questions? This is usually proposed as the way, but it is not really the way. The way is to set up a system of equations. but this is a shortcut to that. And the reason that we like this shortcut is that we can employ the shortcut like right here. We can just take this out and say 3 and 1 is like 4b is equal to 8. So we don't have to write stuff down. We can just go straight from here to saying b is equal to 2. And then once we have b equal to 2, if we can think a little bit further, that would get us a is equal to 5 right away. So, don't always have to pull the numerator aside and write down the stuff that you're plugging in. Get one that's easy and then just kind of like guess your way through the problem. Ultimately, it comes down to this. You have to set your partial fraction decomposition up correctly. Once you get the hang of this, the next step is make it happen. That's it. Just figure out what needs to happen to make that happen. It's the decision here that makes it go. Everything else is just like, oh yeah, just make it work now. You know what you want to have happen. This helps you figure out what those pieces should be. Any questions? After you've done 1,000 problems, which you definitely are not going to be doing, but after you've done 1,000 problems, you start to notice certain patterns. Like the numerators down, or the denominators here both have coefficients of 1. So you're not going to know that a plus b have to equal 7. That's a big clue right there. We're going to start to try to avoid this. We don't want to have to write this down. This is a pain in the ass. We don't want to write that down. But we can see right away that a plus b is equal to 7 because of these coefficients. If there was a 2x minus 3 over here, then we know where that's going to show up. It's going to be 2a plus b. That has to equal 7. So you do thousands of problems and you start seeing those patterns. If you're going to do those 1,000 problems to start seeing those patterns, you have to recognize that you're doing that because you want to learn that. Because there are other ways of doing these kinds of partial fraction decompositions. But if you're going to use a machine to do the partial fraction decomposition, just use the machine to do the integral in the first place. You know what I mean? Yeah, Wolfram Alpha will do a partial fraction decomposition for you, but shit, just use Wolfram Alpha to do the integral for you if you're going to use a machine. Does that make sense? All right. You're not going to get better at doing integrals by watching a computer do integrals. I really wish that that was the case. I mean, I watch a lot of guitar videos on YouTube. I am still not a very good guitar player. It turns out to be a better guitar player, you have to fucking play the guitar. Damn it. Thought if I just watched a bunch of videos and tinkered with my gear enough, I would get better, but oh well. What can I say? Soldering pickups, rewiring guitars, and building pedals is a lot of fun. Maybe that's what I really want out of the whole situation. Next, we need another example. So I need to cut to a commercial break because I forgot to bring the Post-it note with my next example. I don't have B-roll to play for this, so just imagine this is like the part of the drive-in where they have like the snacks. It's like, oh, let's go out to the lobby. Let's go out to the lobby. Let's go out to the lobby and have ourselves a snack. Now you're looking at this as like, oh, dude, you couldn't do that in your head. I'm like, well, I absolutely could not. Because I would forget what I had written down in my mind. So I'd have a 2x squared plus 5x plus 2 minus 15. I knew the negative 13 was going to be the same, but I was not going to break 7 up in the right way. I don't know why. I always break the 7 up in the opposite way. And it messes everything up. let's also multiply this out. We'll have x cubed minus 3x squared plus x minus 3. All right, welcome back from the commercial break. Let's pretend that we don't see that I just worked out what the next example is going to be. Actually, secretly, I totally want to see this because the point is we want to look at, we see a rational function. We want to see this in the context of integration. We want to see this in the context of integration. And the goal is we're going to rewrite our rational function as the sum, 2 over x minus 3 plus 5 over x squared plus 1. The reason that we want to do that is that we know these two integrals. So here is us looking at the y of doing this. And so we can see what our integral is going to be. Once we have this broken down, then this is pretty easy. Because we break it down into integrals that we recognize. This is why we're going to do this. So this here is why we want to do this partial fraction decomposition. Notice that the calculus part is just stuff that we recognize. This is easy calculus stuff, messy algebra stuff. Let's flip the page and take a look at this rational function and think about the algebra that needs to happen on this. I already forgot what it said. So we got 2x squared. So I'm going to take out the integration parts and just write our fraction. 2x squared plus 5x minus 13 over x cubed minus 3x squared plus x minus 3. When we're analyzing a rational function for integration and thinking of the three algebraic things that we might have to do, long division, completing the square, partial fraction decomposition, we have to think about why we have each of those three things. First one, long division. That happens when the degree of the numerator is greater than or equal to the degree of the denominator. That is not the case here. I'm going to make a note of it. We don't always have to make a note of it, but we do have to think it. We have to think, we don't need long division. I'll make it more fun. So I go, oh, good. We don't need to do long division. So let's be relieved. Don't need long division. The degree of the numerator is strictly less than the degree of the denominator. It's only the second day of partial fraction decomposition, so let's remind ourselves why that is. We look at the denominator, see that the denominator is cubic, and we say, well, we are going to have to do some partial fraction decomposition. If the denominator is degree greater than 2 or quadratic with real zeros, then we need partial fraction decomposition. Now we got to remember what a third degree polynomial can break down into. A third degree polynomial has to have one linear factor, but we're either going to have one linear factor and an irreducible quadratic, a one linear factor and a quadratic with complex zeros, or three linear factors. Those are the only two options. We've only got three. Complex conjugates have to come in pairs. So complex zeros always come from quadratic factors with real coefficients. So it's either three linear factors or one linear and one quadratic with complex zeros. Those are the only things that will happen with a third degree polynomial. We know we have to have that one linear factor, at least one linear factor, because it's a cubic polynomial. As x goes to negative infinity, this polynomial goes to negative infinity. As x goes to positive infinity, this polynomial goes to positive infinity. Therefore, it has to cross the x-axis somewhere. It has to have one real zero because of the odd degree. Therefore, it has to have one linear factor. Right now, we're just hoping it's a nice rational linear factor. But we know that it is because we saw what this one came from. Question? I bring that up because it's a nice reminder of some algebra that you may not have talked about in great detail. We do have to factor this polynomial, and fortunately for our heroes, we've seen where it comes from. Lucky for us, this was easy to factor. Next, we're going to set up our fraction decomposition. Each factor of the denominator contributes a term to our decomposition. We see in this case, we ended up with a linear factor and a quadratic with complex zeros. We got the optimus prime of quadratic with complex zeros. Once we set up the terms in our decomposition, we write down the numerators. Above a degree 1 numerator, we put a denominator, we put a degree 0 numerator. Above a degree 2 denominator, we write a degree 1 numerator. We know that all we need out of this is the constant because we know where this came from. But in general, we're going to pretend, but for practice, we're going to pretend that we don't know where this came from. And above a quadratic, we put a linear. Above degree 2, we put degree 1. And then we're just going to solve to make this happen. We just have to multiply, we just put these together. Solve a times x squared plus 1 plus bx plus c times x minus 3 Now, at this point, we could multiply this out, set up a linear system and solve for A, B, and C that way. But I'm going to guess that you want more practice with the shortcuts. Not because you're trying to avoid work, but you're like, oh, that shortcut was kind of interesting. Could we practice that a little bit? Then it sounds like you just want to learn stuff rather than like avoid work. But I know the truth. You want to avoid some work. So let's avoid some work. We're going to do the shortcut. What we want to notice about this one is that I'm not going to be able to take out the A with any choice of any real number, right? I can't plug in something to take the x squared plus 1 and make it 0. Okay, we could plug in I, but we're not going to do that because it would put i's all over the place. What a mess. That would make things worse. We're still going to do the same thing. We're going to make convenient choices for x and see what happens. Here's a very convenient choice for x. If x is equal to 3, that takes out b and c. I like that. So my first shortcut is we're gonna let x equal 3. Because that's going to take out the bx plus c, and we're just going to have 2 times 3 squared plus 5 times 3 minus 13 is a times 3 squared plus 1 plus, it doesn't matter. Those all get zeroed out. Now we've got an equation with just a in it. So I get, let's see, 3 squared is 9. I'm going to have to write this down. 9, 18. And it's going to be 15 minus 13. So 20 is 10a. A is 2. Secretly, we knew that already. Now, at this point, we can't pick values of x that cancel stuff out so easily. So we're just going to have to pick some more values of x. If I do take x equals 0, that will take out b, and it's pretty easy to plug in. So I have 2 times 0 squared plus 5 times 0 minus 13. I know what a is. I'm going to fill that in. 2 times 0 squared plus 1 plus b times 0 plus c times 0 minus 3. Zero, always a popular choice for plugging in. So over here, we get negative 13. Here's going to be 2 plus, let's see, negative 3c. So negative 3c is equal to negative 15. C is equal to 5. We knew that was headed this way, so. Remember, we're pretending that we don't know that b is equal to 0, so let's make sure that we find out that b is equal to 0. We just wiped it out by letting x equal 0. So we need to pick some other value for x. It could be anything that we want. I'm going to pick something easy like 1. 1 seems to be fine in this case. 1 will be good. So I have 2 times 1 squared plus 5 times 1 minus 13 is, we already know what a is. So 2 times 1 squared plus 1. We're looking for b. We know what c is. So I'm just going to go through and plug in all the information that I have now, and then let x equal 1. This will tell us what b is. So here we get 7 minus 13 is -6. This is equal to 2 times 2 is 4. 1 minus 3 is going to be -2b. And 5 times -2 is -10. Did I mess something up? This is why I shouldn't do calculations in front of people. That's so 2, 4. 4 minus 10 is, oh, no, this is fine. It's a -6. That was close. So here we get 4 minus 10 is -6. So we add 6 to both sides. We end up with -2b equals 0. And so b is equal to 0, just as we had foreseen. So those are the things that we want. We see that 2x squared plus 5x minus 13 over x cubed minus 3x plus x minus 3 is equal to 2 over x minus 3 plus 0x plus 5 over x squared plus 1. We have the partial fraction decomposition. So the integration becomes trivial. Oh, I made the wrong face up here. I'm actually kind of happy. Because it took out the B and the C. So this does raise a question. What if our cubic isn't so obviously factorable? In this case, it was obviously factorable. I'm not talking about the fact that it's factorable. The factors are obvious. Because this was clearly just multiplied by grouping. But we could clearly just factor this by grouping. X cubed minus 3x squared plus x minus 3. All we can factor out of the front half is an x squared, leaves an x minus 3. So we just factor a plus 1 out of the x minus 3. So what if the factors are not so obvious? We do know that it's a cubic, so it definitely has one real zero. So a cubic has at least one real zero. We are hoping that that real zero is rational. And I don't know if you saw it in the chat, but it says, can we use synthetic division to find the factor? Absolutely. But it relies on us hoping that that real zero that we know it has is rational. Now you have the advantage of being in a math class. So every time I hand you a cubic polynomial that you're going to have to factor, it most definitely has a rational zero. Definitely has a rational zero. But you do have to figure out which one it is. So we hope the real zero is rational. We're in math class, it will. We are hoping that this real zero is rational. Since we're in a math class, the real zero will be rational. But then we'll have to find it. So oh. So we do know that a cubic will always have at least one real zero. We are going to have to hope that that real zero is rational. And then we can use the rational zero theorem and division, either long or synthetic, to find out what it is. So this polynomial here leads with a 1 and ends with a 3. So our possible zeros are plus or minus 1 or plus or minus 3. We only have 4 to check. I mean, we know which one it's going to be, but there are only 4 to check if we didn't know. So here, for those of you who don't remember your rational zero theorem, the possible rational zeros are plus or minus 1 or plus or minus 3. It's anything that's a factor of the constant divided by a factor of the leading coefficient. Factor of the constant over factor of the leading coefficient. So you can use long or synthetic division to check each of these things. X minus 1, X plus 1, X minus 3, X plus 3. You're looking for a remainder of 0. You could also just plug each of these 4 numbers in to find out which one gives you 0, but then you'll have to do the division anyway to find out which one, what the other factor is. Now, we could look up the factorization on Wolfram alpha, but if we're going to ask Wolfram alpha for anything, let's just ask it for what the integral is. That would be ridiculous to bring technology to bear on just one part of a very long process. If you're starting to wonder why anybody would want to do this, no one wants to do this once they're out of Cal 2. After you get out of Calc 2, no one will ever ask you to do partial fraction decomposition ever again until your kids are in calculus. And we, most likely, are doing the same curriculum that we've done for the last several decades, despite the fact that we're all carrying around massive amounts of computing power in our friggin' pockets. What can I say? It changes very slowly in academic settings. So we made the numerator bx plus c because one of our denominators was a quadratic with complex zeros. I couldn't factor it anymore, right? So we don't know what the numerators are going to look like. In this case, we didn't need the x term, but in general, we might. So we have to be prepared for that. The best way to practice this, by the way, for those of you who want to practice this, is to actually build out your own. So my suggestion is to take like just the one we had, 2 over x minus 3, and then have like x plus 5 over x squared plus 1. Add those together and then use partial fraction decomposition to break them apart. That's the best way to train. Write your answer, add them together, and then break them apart with the technique that you're practicing. That way you're not just coming up with shit at random. That doesn't factor. Okay. Well, this seems like a lot of algebra that we're never gonna have to do again. I'm like, oh, yeah, it's pretty much easy. It's not about doing the algebra in the future. It's about understanding how stuff works. All right, that's gonna do it for today. That's gonna do it for this week. I'll see y'all on Monday. Everybody have a good day, and thanks for playing.